Hello, good evening. Am I audible? Can you hear me?
Yes, sir, you're audible.
So, let's start the session. Uh, Welcome to week 6 of the live interactive session of the fabrication techniques for MEMS-based sensors, a clinical perspective. The course instructor for this course is Professor Hardik Jitendra Pandya of IISc Bangalore, and I am the PMRF teaching assistant Vikas Pandey from IIT Jodhpur. So this is a brief about me. You can reach to me on my email or you can check my portfolio for details. And the schedule is Tuesday 6 p.m. to 8 p.m. And all the recording of these classes are also available on the YouTube channel mentioned here. So before moving towards problems or questions, if you have any doubts related to previous week, if you have any doubt related to previous week questions or anything taught, you can ask. Yes. Any questions you are free to ask. Okay, so let's move towards questions. Okay, and throughout the session, you are free to unmute yourself and you can ask questions or doubts. You can stop me anywhere, not an issue. Okay, so let's come to the first question. The photoresist layer is exposed to visible light, ultraviolet light, infrared light, or LED. What will be the right answer?
So option A.
Option A, visible light. Okay. Any other answers?
Ultraviolet light. B, I think
Ultraviolet.
B.
Yes. Uh, In fact, we can go with visible light also, but the problem is that visible light, the wavelength is too big for our critical dimensions. That is why we go for ultraviolet light. Okay, this is the preferred one, and generally we use 365 nanometer wavelength and 456, I think, yeah, 456 nanometer. This one I am not sure, but 365 nanometer, like there are two general wavelengths, and both of these fall in the ultraviolet range. Okay, so ultraviolet light is the correct answer. We will see, like, there are some more questions related to this and how we can even improve the resolution beyond the one given by ultraviolet. We will see that. Okay, so now let's come to another problem. The base resistance value of chrome gold ID structure. So on the top of the SiO2, there is chrome deposited, and above it, gold is deposited. Okay, above it, and we are forming an ID structure, interdigitated electrode structure. Okay, and it is saying that spacing of 50 microns and 15 microns. Like there are two different IDA structure. This is one and this is two. The gap between this in the first case is 50 micron or 50 micrometer, and the second one is 15 micron. Okay, and the resistance given by this one is X ohms and the second one is Y ohms. So what will be the relation between X and Y? What will be their uh, values, or how can we have a comparison between them? So the first option is the X resistance, like the resistance of the first one is less than the resistance of the second one. Resistance of the first one is greater than the resistance of second one, or both of them are equal, or both of them are zero. So what can be the correct answer? Yes. It's fine, even if you are wrong, we will discuss how it is happening and why it is happening. So feel free to.
Sir, is it A? X. No, is it B X greater than Y?
What may be the reason for this?
I think it's because the area between the
Mhm.
electrodes is greater, so resistance will be high.
Okay. Like the length, what we generally understand is that if the path to travel is more, the resistance is higher, right?
Yes, that's what I'm saying.
Okay. Yes. Any other answer? Okay. So here the thing is that now remember when we in the first class itself when ID was introduced, we know that in fact there is no path between these two electrodes. This whole area is an insulator. Like there is nothing between them. We are depositing SiO2. Here also I have mentioned silicon dioxide, which is an insulator. Okay. So now taking in view this one, will your answer change that it is a complete insulator? What is the resistance of an insulator? No, you can speak like messages. I will not be able to check every time. Okay. So you can speak, not an issue. Okay. Yes.
Okay, so an insulator, the resistance is 0.
No.
No, so
Very
it's
high.
very high,
It's very high. It's not zero. Okay.
not 0.
Yeah. So it's very high. That means there should be no current flowing between them, right? The resistance is
Yes.
very high. That means no current. Current is zero, right? And similarly for the second one also it is zero. So will there be any difference between the resistance?
No.
No, they are equal. But ideally, if you check, there will be some difference, very slight difference, you can say, but they will approximately be in the same range. Okay, like mega ohm or giga ohm range. It is an insulator. So it will be high Z or high impedance. Okay, and why is it so? Because there is no path for the current. Fine. Any doubt in this?
No, sir.
Clear? So
Yes.
whenever we have open wires, right, like two, it is simply you can understand that we have two wires and they are not connected. They are lying at some distance. So what is the current or resistance between them? The current is zero and resistance is very high. There is no, in fact, almost the whole current is being stopped. That is why it is very high. The similar thing is here. But how can we make this conductive? Like in our sensor, we are making this area conductive. And how are we doing that? Any idea?
No, sir.
We are using the functionalization material, right? Like ZNO or any other functionalization material that is having the property of having some changes when it comes in contact with the analyte. Fine.
Yes.
Which layer it is, sir? It is?
Yeah, what you are saying? Hello?
What's the name of that layer you said? Function,
Functionalization layer. There can be some
functional.
other terminology also because sometimes what happens is that uh, if we are using similar names and when you publish, it may uh, catch in flag. So some people are using some other terms like decoration. Some people are using like deposition. Some people are using functionalization, but it is generally known as functionalization layer. Okay, you may get some different terminology also. Small differences can be there.
Okay. Okay.
Okay, so the correct answer is X and Y are equal or comparable and have very high impedance. Fine. For the measurement of electrical properties of a tissue, a device is fabricated. What are the process steps to be followed? So here what we have to see is that we are measuring the electrical properties of a tissue. Okay, so what are the electrical properties we can measure? Yes.
Say
Any,
elasticity, resistivity, conductivity, I say,
yeah, elasticity.
and thermal.
Yes. VT and thermal. There are three parameters we can check using this. And of this, the most easily we can do is conductivity or the impedance or the resistance. Okay. And for that, we are making this ID kind of structure. Okay. So what steps are to be followed? Like what is the sequence of the steps? Any answers?
No, sir.
Like this one, these are the steps you have to arrange it.
Wafer cleaning first, then
First,
oxide deposition,
okay, yes.
then
Mhm.
then first metal fabrication to fabricate heater and then ID. That is what
Yes,
I felt.
yes.
Just
The sequence is right. I will tell you one second. Okay. And like this is something not everyone will say, but what I understand is that whenever we are talking about fabrication steps, it is very similar to cooking. Okay. So in cooking also we first go for cleaning the vegetables. Okay. So the first and the foremost step everywhere will be cleaning. Okay. And here also, like when you actually do the fabrication, you will find that it is very similar to cooking, like in sense that if you overcook something or undercook, it will taste different. So very similar to that, when you are doing fabrication, if you are like you are going a bit more, like you are doing some step more than required, it will get damaged. If you are doing something less than that, it will have some problems. Okay. So it is very similar to that. And so every time, whenever it comes, the first step certainly is wafer cleaning. Now what we want is that on the wafer, we want that first we make a heater, okay? Structure like this. Now on the heater, if we deposit another metal, what will happen? Metal heater is there. On top of it, we are depositing another metal. What will happen? Yes. Any answers? If there is a metal structure, like if we have something like this, say, and then I am putting uh, another metal above it. What will happen? I'm putting a metal above it. So will it remain what it was supposed to be?
no.
No. What will happen? It will get sorted. Everything will get sorted. To isolate it, what we are doing is that we are putting an insulator, and in this case, generally oxide. Okay, and then on top of it, again we are creating our other structure by depositing metal and patterning it. Okay, so here two steps are actually missing in this. They should also be there. One, then this will be the next, and after this, in this itself, it will be patterned. And if it is not patterned, there is one another way. And okay, then is the oxide deposition, and then is metal deposition to fabricate ID. But here patterning has been skipped. That is using lithography. So there is sometimes when we are going for bigger dimensions, like that is not in less than 200, 300 micron. If something is more than 200 or 300 microns, we can even go for deposition directly using shadow mask. Like we can have some steel or chromium mask which have cutouts. Like we have a mask very similar to lithography mask, but that is on a glass. Here it will be, whole thing will be metal and some pattern is cut out from it. Okay. And it is put above the silicon wafer. And when the metal deposits, the metal will deposit throughout, but only the pattern will get deposited inside. Other part it will deposit on the mask, and we can clean the mask. Okay. So in this case, what is being done is that wafer cleaning, then metal deposition to fabricate heater. The heater pattern is being deposited, say by this shadow mask. It is called shadow mask because it creates a shadow kind of structure. It will mask out everything, and only the part where it is open will get deposited. Then we are going for oxide deposition so that it is covered. It does not sort out in the next step. Okay. Then is the metal deposition to fabricate ID. That also can be done using shadow mask. Fine. Clear? And one more step I have added here, that is oxide deposition. In fact, like there are two oxide depositions here. Why? The first one is, remember when we were talking in the previous example also, that silicon on it, we are putting SiO2 first. This one is also to ensure that it does not sort. So in that case, and then we deposit the heater, then we put SiO2 over it, and then we deposit ID pattern. Fine? Any confusion in this?
No, sir.
Clear?
Yes.
So we can move forward, right? Properties measured using ETM sensor. ETM is for breast cancer tissue phenotyping R. Capacitance, elasticity, specific heat, capacitance, viscosity, thermal conductivity, resistance or resistivity, elasticity, thermal conductivity, resistance, resistivity or viscosity, and specific heat. What will be the correct answer? In fact, in the name itself, if you
C.
see, because we have discussed earlier also, like there are three things we are seeing: resistance or resistivity. The second one is elasticity, and the elasticity, that is the mechanical properties. Resistance or resistivity, that is the electrical properties, and thermal property, that is thermal conductivity of the tissue. Okay. And in fact, if you remember the name, it is electrothermomechanical sensor. So there itself, it gives the answer. Okay. Now, let's come to next question. Su8 is a negative photoresist. We have talked about this in the previous classes also. Areas of wafer covered with Su8 when exposed to UV light will harden, soften, remain same, cannot be determined. I think this is a repetition from previous class.
Yes.
Yeah,
So harden.
it will harden. So the exposed area hardens and unexposed area will be removed. Okay, and this is exactly opposite to a positive photoresist. Fine. So since this is negative, whatever we expose, that will harden. Fine. Okay. A typical photolithography process. This is about the not about the whole fabrication process. This is only about the photolithography process. Involves the following processes. Put in correct sequence. Spin coating the photoresist, mask loading exposure, stripping photoresist, etching, soft bake, hard bake, and developing. So what can be the correct sequence? Yes, anyone? At least some part you can say, right? So what can be the correct sequence of photolithography?
Mm.
So I don't know the full answer, but my answer is spin coat the photoresistor first,
Okay.
mask loading,
Mhm.
then etching.
Okay.
After that
So,
developing,
okay.
developing,
Developing. Okay.
soft bake,
Okay.
then hard bake, and lastly stripping photoresist.
Okay. G. Okay. Very much correct. Like a small correction is there, other things are correct. Yes, Nilima, would you like to add something or change something?
Uh, yeah, I feel like that first will be the mask loading and exposure will be there. Then later on, it will be soft baking, followed by spinning.
Mhm. Okay.
Then so that what I'll say, the etching. Then again the
Mhm.
hard baking will be there, and then
Mhm.
stripping of the photoresist, followed by
Okay.
developing. I'm not so sure about.
Okay. Okay. So let's see uh, how it is done. We will take a wafer, okay, and on it we put something that is photosensitive, okay. So on this wafer we will pour something. I think I have not, yeah, I have not put the picture. Okay. So I think here we have space, okay. Don't say this for now. Let's understand what is done, then we will check. So on this wafer we pour some photoresist and we spin it at a very high speed. So what will happen when we do this?
So uniformly, it will
Yes, it will
spread
get
over that.
coated uniformly. But this is a liquid, okay? Even though a very thin layer of it will form liquid PR, okay? Will it be solidified very easily? It will not be in solid state, right? So what we do is that just after doing this, we heat it a bit, not very hard, but very slightly. So then comes the soft. First is spin coat, okay. Then comes the soft bake. And why soft baking is done in the previous class also, I think there was a question why it is done. It is done to uh, remove the moisture. Like still it will have some moisture, so moisture removal is done. Fine, moisture removal, and so that it will not fall, or if you hold it with something, it will not stick to something else. So this is just that we are putting a resist. Then what we do is that we put it into the actual mask aligner. We align it, expose it. Once exposed, what happens in exposure? Let's suppose it is a positive photoresist. So what will happen in exposure? Which area will become soluble? Yes, I'm audible, right?
Yes, sir, you are audible.
Mhm.
Uh, so the like except that pattern, whichever the portion is there, that will be
That will
solved.
become dissolved, like that
Dissolved.
will dissolve easily. And in what it will dissolve? It will dissolve in something that is a developer. This is very much like the, if you have heard or seen about the previous photography technique in which in a dark room it was developed, like negatives were developed. This is very similar to that, and in fact this whole process is also done in a dark room, a yellow lighted room, so that no other light can expose it, okay. So then it will be developed. Now we will be left with the pattern and nothing else. Now we want that for the next steps, this pattern is hard enough and it does not dissolve in something else. Okay, so to do that, we go for hard baking. And in this case, it will be hardened, like it will be fully hardened so that it does not come out very easily. Hard bake. Okay, and then we go for etching of the metals. And if we are not doing the hard bake, what will happen is that during this process, etching process, there this resist can get etched. So to protect it, we are going for the hard bake. Once etching is done, now we are not in the need of the photoresist. But since we have already hardened it, it cannot be removed very easily. We will have to go for some special chemicals. And generally, in case of positive photoresist or even in negative, acetone works fine. Okay, so we go for stripping, PR stripping, and our structure will be made. Fine. Any confusion in this?
No, sir.
Clear?
So for
Yes.
So
stripping purpose, acetone is used.
generally, like there, either you can go for acetone or some photoresist even come with a specific stripping solution. Like uh, mostly there will be combination of two or three things. Like when you are buying a
Okay.
photoresist, always
Hmm.
remember that when you are buying PR, along with that, you will have to buy the compatible developer and compatible stripper.
Okay. Okay.
Okay, like you cannot go with any developer will work for any PR. That is not so. Okay, so PR developer and stripper are generally in combination, and in most of the cases, you can strip like you can skip the stripper if it is not a very specific kind, because in that case, like acetone works. Okay. Bye. Along with it.
Okay.
Okay,
Okay.
so we have seen Su8 material being used in the device fabrication in the ETM device, as well as the piezoresistive microcantilever device. Which of the following statements are true in this? Su8 pillars were used in the ETM device to ensure electrical contacts to ID. Su8 was used in the piezoresistive device to transfer force onto the piezoresistive material. Which of the following is true? Yes, any answers?
B
B.
was
It
used in
was
piezoresistive device to transfer.
to transfer force onto the piezoresistive material. This is right. As well as SU8 pillars were made and they were coated with this chrome gold to make it conductive. Have you seen that
Okay.
part? Yeah. So,
Mm,
uh, to ensure electrical contacts to the ID.
on- okay.
Okay. Like so that we can have good a proper contact with the ID patterns. This was used. Okay. This is something from the like lecture. Okay. Uh, just yeah. So silicon on insulator is a special type of silicon wafer. Evaluate whether the following statement about silicon on insulator wafer is true or false. It has thin layer of silicon over a thick layer of silicon separated by a thin layer of insulator such as oxide. Okay, so what it is saying is that this having a thin layer of silicon, okay, over a thick layer of silicon. So there is a thick layer of silicon, and in between there is something which is an insulator. Is this true or false? No, insulator or oxide is there. Yes.
So means you mean to say that silicon is there, then on
Hmm.
top there is a, on the thick layer of silicon there is a insulator or oxide, and then again Si is used.
SI is there.
Si is
Yes.
kept.
Yes. So, is this what is
False.
silicon on insulator?
No idea, sir.
Oh. So this is a special type of wafer, and seeing it, you can say that how will we make it actually? This is somewhat very difficult, right? And that also we want that it is of the same plane as this silicon. Okay. So what generally is done is that like though that part must is not taught in the class, I am just telling you, like you take two silicon wafers, oxidize them. So a a silicon dioxide layer will be here on top and here on the top. Okay, and then we bring them together, and using some force, if we keep them together, they will stick. Like oxide and oxide part will stick. Then we will have a oxide, and then silicon this side and silicon this side. Okay, then easily it can be cut from here, like it can be chipped out, and a thin layer of silicon is left, and a thick layer of silicon remains there. Okay, and it is bonded by oxide, and this layer has the this has the advantage that this lower silicon will not, this bulk silicon will not be affecting the upper conductivity and this thing. So whatever devices we want, we can fine tune the properties in this area on the top itself. Fine. This is special kind of uh, wafer that we get, silicon on insulator, and there is one more, uh, silicon on nothing. In that case, this area is actually etched out. It is made and etched out, so it will be like air gap, and it is supported by some thin pillars of SiO2, very thin nano pillars. So it is like pillared structure, almost like air is there. Okay, so these kind of wafers are there. Fine. Are you getting it?
Yes. So I have a question then, that
Yeah.
as on the top, whatever the silicon is there, it is deciding the properties. Then what about the base? At the base, there is a thick layer of silicon. Na?
Yes.
So what is the use of that then silicon? It may be a silly question, but what is like?
No, it is not a silly question. It has a lot of effect on this. The first thing is that whenever we have two two plates, like two conducting things, and in between an insulator, what it forms?
Two conductive part, and one is
In between there is an insulator. If we uh, rotate it and we see it like this is an insulator, and then silicon and silicon, both of them, silicons are
the
like conductive.
conductors.
Yeah.
Mhm.
So is not it like a capacitive structure, a
Yeah,
capacitance?
yeah, yeah,
Okay.
yeah, yeah. Okay,
So
yes, yes.
so in this case, what is done is that sometimes if you have like not specifically in case of sensors, but if you are going for MOSFET and this kind of devices, uh, there you might need to control the back voltage. Okay, the back voltage will have this effect that it will create a barrier here. okay,
Hmm.
a capacitive kind of structure. And in that case, we can control the channel. If you study a bit, like you are from electronics background, right? Or
Mm-hmm.
instrumentation.
Instrumentation.
Okay, so you must have a bit of idea about what is a
Source,
MOS. MOS.
MOSFET. Yes,
Yeah.
yes, yes.
So
Wait.
in case of MOS, what we generally know is that with gate we control. We study
Hmm.
that, right?
Hmm.
But
Hmm.
there is a very big problem that occurs is that if the back side of the of the structure is not properly grounded, the effect is changed. There will be some leakages, gate leakages, and other things occurs. The
Hmm.
barrier gets no, the exact barrier that we want that will not form. Okay, so to overcome those problems, this is used. And in this case, what will happen is that if we ground this, these charges will come out. This will become zero, and this capacitive, like whatever depletion region was formed here, that will automatically go out, and it will create a very good path for us. For MOSFET kind of structures, this is very useful. FET and MOSFET. Okay. And
Okay, sir. Thank you.
silicon on nothing is even more advantageous because there is very less this the dielectric constant is also high, as well as there is very less contact. Like in this case also, even though it looks like it is isolated, but there will be some flow of the
Okay.
charges. Okay,
Mm-hmm.
so it is not like if it was not there, still it would have been okay. It has some effect, not some, it has a great effect. And this I remember because during my masters, what I did is that I exactly thought like you, what is the purpose of this? Okay,
Yes.
so I tried to remove it. Like I created a device without it. Like I was working on SON, silicon on nothing. So I tried one without this bulk silicon and one with bulk silicon, and in both the cases the results are quite different.
Okay.
Okay,
Okay.
so there is difference. So this is special kind of wafers in which they are separated by an insulator. Okay, an ID fabrication in ID fabrication process or any other fabrication process, acetone dip is done to remove gold, nichrome, chromium, or photoresist.
Photoresist.
Photoresist, right? We discussed it,
Yes.
right? So this is the stripping part. Okay, and in some very specific cases only you will find that actually acetone is not effective, and in that case you can go for some specific strippers, or generally if you have adequate resources you go for stripping, like a stripping solution. It's fine, it is anyway acetone only. Okay. Okay. Whether the following statement is true or false. For SU8 photoresist, development is followed by hard bake. Is it true or false? Yes. Any answers?
Yes, true.
It's true. Because we have already seen,
Seen. Yeah.
yeah, that once the development is done, whatever is left, we want it to be stable and hardened. And that is why we go for the hard bake. Okay. There's like there sometimes people get confused that hard bake it should be at a higher temperature and this thing. Okay, so there are some cases in which you will find that this soft bake is being done at say 115 degrees Celsius, and hard bake is being done at say 90 degrees Celsius. Okay, so it is fine. What will differ is that in this case, say it was done for 60 seconds, in this case it is being done for 90 seconds. Okay, so from the name, don't think that it is soft bake, that means at lower temperature, and hard bake it
Temperature.
will be at higher temperature. It is more about what effect it is having. In case of soft bake, it is just removing the moisture. Okay, in case of hard bake, it is making the uh, left pattern stable, like for further processing, so that it does not get removed easily. Fine. Okay, sorry. Development is followed by hard bake.
So the answer
Oh,
is
no. Yeah, it is false.
so
We are talking about SU8, right?
it's a negative photoresist, right?
Negative. Yes. In case of SU8, it will not be. Yes.
Okay.
We are talking about SU8, right? So, there are some variations. Okay. Like in case
Mm.
of negative photoresist, it will be first hard baked, then it will be developed.
Okay.
Okay. Uh, because uh, the structure that is exposed is removed, right? So hard bake actually makes it easy to remove. In case of negative, it will be opposite. Yeah, forgot. We are talking about SU8, right?
Yes, you. Oh, yeah.
Yeah. In case of negative, it will be opposite. Since we have to remove the exposed area. Uh, not, yes, we have to remove the exposed area, not the unexposed area. Or no, I am getting confused. In case of negative, uh, the exposed area remains. In case of positive, exposed area is removed. Yes. Is it right? Is it right now? For case of in case of positive, the exposed area is removed, or it remains. Yes. Hello. Am I audible? Hello.
Hello.
Yeah. Am I audible? Is this
Yeah.
correct? Is this correct?
Yes.
Like,
Yes. Understood. Okay.
yeah. Actually, I also got confused. Okay. So, yes, SU8 is a polymer insulator negative photoresist, or all of the above.
It's a negative photoresist.
Yes, this is correct. Any other answers? Remember in one of the class I was talking that photoresist generally have three components: a resin, that is a polymer, okay, a binder, and a photo photoactive material.
Yes.
Okay, so uh, it is a polymer. SU8 itself is a polymer. It is an insulating polymer. It is not conducting. Okay, and that is why when we are creating these pillars, SU8 pillars, we are coating it with gold. Why? So that we can have some conducting path. If it was already conducting, we don't need to do that. Okay, so it is an insulator as well as negative photoresist. So it is all of the above. Okay, what kind of mask would you use while doing photolithography to form SU8 pillars? bright field mask or dark field mask? Yes. What kind of mask will it be? Bright field or dark field? Whenever we are talking about the field of the mask, that means what the maximum area is, how the maximum area looks like. So if we are having the pattern as dark, okay, like suppose this is the pattern, and the other part is transparent. So it will be a dark field or a bright field. Yes.
Dark field mask then it is.
No.
Sorry.
The when we are talking about field of the mask, that is the maximum area. Since it is
Then it's
transparent,
a transparent, so it's a
yes,
bright.
it is a bright field mask. Okay. And the opposite of it, if we have something which is fully dark, but we have the pattern cut out, okay, that is a dark field mask because the maximum area is dark. Okay. So in case of forming the SU8 pillars, we want small pillar-like structure to remain, other part to be removed. Okay. So what kind of mask we
Then
can
dark
use?
field mask.
Dark field mask because it is a negative photoresist. So the exposed area will remain, other area will get removed. Okay. So we can have a complete dark field with some circular structures. Okay. So only the exposed area will remain. That means when we will expose it, this area will remain, other area will be able to dissolve. Fine. So it will be a dark field mask. Fine. While coating
That
SU8 pillar,
means hello.
yes, yes,
That means as it is a SU8 negative photo PR material is there, so
yeah,
dark field mask. So if it is a positive one, then in that case we have to go for bright field because that maximum area needs to be
yes,
removed.
continue. Yes, when uh, we have, according to this, like the pattern will also determine what kind of mask
Okay,
we need, right? Uh, yes, for the same structure, if we were going with some positive photoresist, we will go for a bright field mask for the same pattern. But if the pattern is different, like the pattern is something in which case, maximum area has to remain and a smaller area has only to be removed. Okay, the
correct.
same, yeah, same thing for positive. We can go for the dark mask also
Then, sir, in this case, what is the previous question? Then, how the dark field mask will be appropriate? Because your
because
structure is not given to us.
it is SU8 pillars.
Acha,
The
it's
structure
pillars,
is
sir.
pillars. Yeah, we are talking about pillars. So if we are taking the top view of the pillar, what it looks like, it is circular, small circles,
Yeah,
right?
yeah.
So only such structures are to be left. Other, whatever is there, has to be removed.
It's to be removed.
Yes.
Okay, understood.
So that is why we are going for this. And since it is SU, and specifically here, we cannot go with positive photoresist because here the SU8 also plays a important purpose. Here SU8 does not only work as the patterning thing. Along with that, it has some use in the sensor itself. SU8 remains even after the process ends. Okay, so that is why
Okay.
we are going for SU8. SU8 as a polymer, as a resin, also is having some other properties, like even after the whole process is done, it can remain and it can act as some additional it can have some additional functions, and here it is acting as a pillar, okay, to give the conductivity to the IDE pattern.
Okay.
Okay, so SU8 is very commonly used for such purposes, and specifically to make a tank-like structure. Like if we have, I think I discussed in the previous class also, like if we have electrodes and we want that whatever analyte or tissue we put, that does not go beyond this area. Okay, so this covering this tank kind of structure, that is generally made using SU8. Okay, it can be thick resin kind of structure, right? Any more questions on this?
No, no. Understood.
Understood. Okay. So while coating SU8 pillar with chromium gold by thermal or E-beam evaporation, the sample has to be tilted. Is it true or false? The pillars we have made, okay, and we want to coat these pillars. Like if we see the top level, these are the top levels, and at some distance, we want to coat this, okay, throughout, so that it becomes conductive. So to do this, the sample has to be tilted. Is it true or false? You have to cover this almost the whole area. So in this case,
No,
will it need to be tilted?
I didn't understand that. I'm trying to understand what exactly it is.
See,
Failure is
generally,
there. Then
when we are depositing, what we do is that, can you see my hand?
yeah.
Okay. So it is like the wafer is somewhere here, okay,
Yes.
and the metal is here, okay,
Hmm.
and this
Hmm.
metal evaporates and get deposited here, okay,
Hmm. Hmm. Hmm.
and this sample is actually moved uh, around so that,
Hmm.
like so that we have a uniform coverage. In this case, it is saying that this simple setup will not work for it. What you will have to do is that you will have to tilt it like this.
Hmm.
This is the evaporation one, and you will have to tilt it and then rotate it, because we earlier we have a plane surface. Okay,
Hmm.
on it we have to deposit something. In this case, we have a stick-like structure, and that
Hmm.
structure has to be not just deposited something on the top. We have to deposit all around it.
All. Yes. Yes. Then it has
Okay,
to be tilted.
it has to be tilted.
Be
Okay,
tilted.
because then only it will have uniform coverage, and we will have to rotate it, keep rotating it. Then only it will have a complete coverage. Okay, fine.
Yes. Yes.
Okay, so these are
So
very
everything
simple.
is because of the pillar structure only. As it is
Yes,
a pillar, that's why the things are changed, like
yes.
required to be.
Since
Okay.
so, we have to understand that there are some standard processes. Okay, in first we have learned about standard processes, but according to our need, we can have some specific like specific processes. Okay, like in this case, since it is a pillar structure, we have to go for some other structure, and here we are talking about MEMS based sensors. Okay, in MEMS based sensor, we will have some 3D structures, like we will have depth, and we will have some bigger structure, like we will have some mechanical structures like pillar, cantilever, and that. And in this case, we can have some modification in the general microfabrication structure. So That is difference between MEMS and normal microfabrication. Okay. In microfabrication, you will never go for this pillar or what we have seen diaphragm like structure that comes under MEMS. Okay, so if we are talking only about MOS and these things, there we have all the things in the plane. There is no bulk structures. But when we are talking about MEMS and MEMS based sensors, we are talking about bulk based things, like we will have pillars, we will have trenches and such things. Fine. So there can be small modifications. So these are like from normal microfabrication. Now we are taking some specific cases where we are going in specifically MEMS based, like some MEMS processes which are a bit different from microfabrication.
Okay.
They are using the fundamentals of microfabrication only. Okay. Now we have seen that. Next question, that wherever we are coming, we are talking about chromium gold, right? On the Su8 pillar. What the conducting layer is gold, right? We want the gold electrode. But why are we using chromium here? Is it to reduce resistance, for better adhesion, for heat resistance, or for just for aesthetic purpose?
Maybe for better adhesion.
For better adhesion. Because if we deposit gold, it will just peel out very easily. And in fact, if we go for the PR stripping with acetone itself, it will come out. So our whole work will get wasted. So a very thin layer of chromium acts as adhesive, like some structure is there over it, chrome is deposited, but then you can say that chrome itself is a metal, why don't we go for chrome only? Okay, but chrome will oxidize very easily.
Yes.
That is why we cover it with gold. And gold, since it is very good conductor, it will easily work as our electrode. Okay, so it is for better adhesion. Almost in all the depositions, we go for chrome or sometimes titanium also. Chrome or titanium. These are the common adhesion material for gold. Okay. What is P dot PSS? You have heard this name, right?
No, no.
No?
Sorry, I did.
Okay. So its full form is polyethyl, like 3,4-ethylene dioxide thiophene polystyrene sulfonate. Okay. It is a conductive and piezoresistive polymer. This is the one that is used to form the cantilever kind of structure. Okay, since it is piezoresistive, it will have effect with stress. Like uh, if it is pressed or if it is stretched, what will happen? There will be some change in resistance, right? And it is conductive as well. So that resistance can, like, since there will be some resistance under the stress, it will have some change in the resistance. And this is also a polymer, just like Su8. So you see the polymers can have different properties. Su8 is an insulative polymer. In case of P dot PSS, it is conducting. Fine. There are other conducting polymers like polyaniline. Polyaniline is there. There are other many conducting polymers also, and conducting polymer itself is a different field of study. Like a lot of work is being done in that field. Fine. Any confusion till here?
No.
No.
This long form is also yet to be remembered, right? Poly
No.
340.
No.
No, no. Okay.
No need to remember these things. I have just put this
Because it,
in. Yeah. In fact, I believe that
okay.
most of the things you should not remember. You just should know that there is something that exists, because whenever you need, you can refer it. Right? You don't need
Yeah.
to remember all
Then
the
this
chemical.
PDOT PSS, it is a long form of something because that also I haven't come across the term PDOT PSS.
Yeah, this is the full form of this.
That is what is the long form. Okay, 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 okay.
Yeah,
Polysulfonate,
yeah,
polystyrene. Okay,
yeah,
understood.
yeah. So it is the short form for this. I think. Okay. So now silicon nitride is grown over the cantilever for compensating stress in the cantilever due to silicon dioxide. So we are creating a cantilever kind of structure. Cantilever is like a uh, structure floating in the air. Okay. So we have a structure like this. Let's say we have here Su8 tip is there. Okay. And this is silicon. This is the cantilever structure. Okay. On it, SiO2 is deposited. Okay. And then over it, silicon nitride is deposited, Si3N4. So it is saying that this silicon nitride is grown over cantilever for compensation of stress in cantilever due to silicon dioxide. Is it true or false? Yes,
False.
false. So why
Good.
is it grown? Yes,
True.
yes, yes. Continue. Not enough. Like if you have a different thought process, actually sharing it helps me because then I will be next time whenever I will take this, I will be prepared like what other alternate things a person can think. Okay, that is why I need alternate thinking, like what you are thinking, why it is like this or why it is not like this. That helps me also.
My point is that if the cantilever structure as it is shown over here,
Hmm.
like, and on that we are depositing the silicon dioxide. So
Hmm.
already one force is that is putting on that structure. And if we are again
Hmm.
adding that, then how it will help to compensate the stress? Just I am not aware of the silicon nitride, how it helps us, but that is what is my point. That again, then one more layer we are adding. So it will
Yes, it
again
will.
bend it, right? If you are
Yes, it will
talking
bend
about
it.
the stress.
Yes.
So then how it will help to compensate the stress?
Uh, so.
In that case, if it is then from the bottom, if you are putting then the like opposite direction, if you are putting the force, the
Mhm.
material, then it would we can say that it will help to compensate.
Hmm. So yes,
I am not
that is
sure, but
yeah, and in fact that is very logical also when you think from that point of view. But let's think it is a this structure is very thin structure. Okay, so if we have a very thin structure, like if you cut out a thin page, like a thin strip of a paper, what it will do? If you keep it like this, what we want is that ideally it should remain straight, right? But
yes.
if you keep it like this, what happens is that it will try to move upwards,
Hmm.
right? So such uh, like that is actually thicker than
Okay.
what we are
Okay. Okay.
thinking here. So it is due to the stress that is on the top surface there. So here what happens is that such kind of stress develops due to this SiO2. It will
Okay.
try to bend it up. This
Okay. Then in that case, it is correct.
yes, it because you are thinking this structure as a bit thicker structure, right?
Yes.
Yeah,
Yes.
but this is very thin structure. That is, and it has been designed so that it can easily be pressed down or
Mm-hmm.
pressed up according to the stress, like what is the stress, elasticity, and other measurements. Okay, we want that normally it should remain straight, but we are putting it with SiO2 layer. We are covering it with SiO2 so that it remains insulating from the top. No conductivity occurs. okay, and it does not break also. But what it does is that it actually tries to move, like bend it upwards. So to compensate that stress that is developing due to SiO2, is another layer of silicon nitride is put over it. Silicon nitride like releases the stress. Like there are some lattice difference. Like if we have like this is the SiO2 lattice, okay, and I think silicon nitride is having somewhat less bigger, okay. So what it will do is that this interface it will try to like they will try to adjust themselves, and in this process the stress that was forming it will be relaxed, okay. So like a stress was for moving it up, another stress we are putting to move it down. So the resulting stress cancels out and we get a straight structure. Fine.
Okay.
So these are happening at very small level, like in some uh, processes like epitaxy and all. This small stresses play a very critical role. In that case, like what layer you are putting one above another, that can play an important role, and that can create a whole new kind of device. If you have time, just sometime read about this HAMT structure. They are also created. Like you have learned about FET and MOS, right? HAMT is
Hmm.
an advanced form of FETs, like high electron mobility transistors.
High electron mobility.
Mobility transistors. They are being
Okay.
explored now. Like they are somewhat like current topic, and especially for space and other applications. These are something studied being studied. Okay, so they are alter like that is special kind of transistor formed wholly due to the this lattice mismatch. Okay, the
Okay.
stress being formed there, a special structure is formed. So this is a different field of study itself. Okay,
Mm-hmm.
this stress management in case of these materials. Okay, so here silicon nitride compensates the stress. So there is a stress in SiO2, then another counter stress occurs and it gets cancelled out. Okay, now why primer is coated before photoresist? Like whenever we are talking about photoresist, we are talking about like we are putting photoresist here and then spin coating. Okay, but many a times you will see that before photoresist, a transparent, very thin and like photoresist is a bit thick, okay, a thick liquid. A primer is used, which is very thin liquid and a very thin layer of primer is put, and then over it photoresist is put. Like it is then uh, dried and then photoresist is put. So what can be the purpose of this primer? Is it to remove moisture? Is it to keep the wafer clean? Is it to improve adhesion of the photoresist? Or is it to improve the alignment of the mask? Yes. Any answers? What can be the probable reason we are using primer?
Get clean and then improve the adhesion, both B and C.
Improve the adhesion, it's fine. Cleaning, we are not,
Cleaning will not.
yeah,
Okay.
cleaning because cleaning has already been done, right?
Been done. And
Yeah,
acha, okay. Cleaning and then primer
primer,
is
yeah.
then. So it may be then even the moisture, it will help. No,
Mm. Moisture, like in the photoresist,
that is
anyway, there
in
will be
soft
moisture.
bake.
Yeah,
Yes.
that we will go for soft bake. Primer is very similar to the primer we use in our houses. Like before painting, we put prime. What is the advantage of primer? It is a very thin coat, and after that, you must have seen that if you are getting something painted, if you don't use primer, the consumption of paint is higher. If you use primer, the consumption is lower because we can go
Mm.
for thin structure, very thin layer of paint after it. Okay, so very similar to this, it like we are seeing the wafer as such, but there are small roughnesses there. Okay, and if we are putting a very like very thin liquid over it, so it can fill up and make the structure smooth. Okay, and using this, there are two things. One is it will have good adhesion, like this will the primer have good adhesion with the photoresist, and the primer has good adhesion with the wafer. Okay, along with that, we can go for lower thickness of photoresist also. Okay, since we have more smoother surface, we can go for thinner photoresist. And what will be the advantage of going for thinner photoresist? Like if we have very thin layer of photoresist, what can be the advantage you can think of?
It will be easy to strip the like to pattern like to have that pattern. Easy to remove that or stripping will be easier. Means less quantity needs to be stripped.
Okay.
So
No, it's fine. Like I will not discuss it here. I will discuss that later on. I think one more question is there related to that. Okay. So keep in mind there is some role of it.
yeah.
Okay, the thickness of photoresist. So some advantage is there if we go for thinner photoresist. Like if we can go for thin thin value, and if we are not using this adhesive, the primer, and we go for thinner one, what may happen that it will chip out. Like you must have seen that on a dry surface, if you put a put paint, and if it is like very thin, it will chip out. If it is very thick, it will chip out, right? It will come out. So this is very similar to that. Like it is a paint kind of structure, okay? And if you are putting it on a dry, like dry wafer, you can, first thing is that you cannot go for very thin structure because it will not spread easily. And if you go for thicker, very thick structure, it can come out, like it will chip out maybe in some later stages. So this is used to improve adhesion, and HMDS is the common primer that is used. Okay, this is one of the common primers that is used, and it is generally used when you want to get very thin photoresist structure. Okay, any confusion in this? Yes. Any doubts or any questions in this?
No, no.
Okay. Okay. Again, repetition of some question. Mask plate having transparent features and dark background is dark field, bright field, gray field, black and white. We have a mask. The feature is transparent and the other area are covered. So what kind of mask it will be? It is like this.
It will be dark only.
Yes, it will be a dark field mask. Okay. So this, in fact, we have seen many times. Like when the structure is dark, whenever we are talking about field, okay, field, the maximum part is bright, then it is bright field mask or light field mask. The maximum area is dark, that is dark field mask. Okay. What is considered as the gold standard for breast cancer diagnosis? ETM phenotyping, MRI, mammograph, or X-ray. If you are going for breast cancer diagnosis to check whether breast cancer is there or not, Which of the
It's
following?
mammograph.
Mammograph. Okay. So mammograph is used to detect. Okay. So let's check. Like this, the general. Like I got it from somewhere. I have actually not seen mammograph. Okay. So the tissue is pressed, and then X-ray is used to image that. Okay. But it has some problems. That X-ray has some limitations. What limitation X-ray can have is that X-ray cannot go beyond like some, you can say it has some resolution that we can get. We cannot get a very perfect. Okay. So to confirm whatever has been
Mm.
seen in mammogram,
Mm.
MRI can be done. If,
Mm.
but not normal MRI. A MRI similar to mammogram. Okay. Like the same thing where the tissue is pressed and then MRI is being done. Okay, so that is the gold standard. Gold standard means that is used to confirm. Like if you have something in X-ray mammogram, to confirm whether it is there or not, you can go for like for complete conformity. It can be done using MRI. Fine. So
Mm.
MRI is the gold standard. These all are the way of
Okay.
diagnosing the breast cancer, but mammography is the common one that is used. But if you have like if there is some chances of positivity in mammography, to confirm it, people go for MRI, and then for other kind of like uh, other uh, other tests and all. Okay, and these are used for early diagnosis. Okay, even before it has developed into a full-fledged cancer. Okay, what strategy was used to make Su8 conductive such that it functions as an electrode? I think we have discussed this. This answer you must already
Gold
know.
coating.
Gold coating. Su8 is not a conducting polymer. It is not mixed with P dot PSS. Since we are actually coating it, we cannot mix it. Okay. We are doing it with gold coating. Like we are doing the spin coating, lithography and all, and then we are going for the gold coating. Okay. Then the final resolution in photolithography can be obtained by using blue light, UV light, IR light, or X-ray.
UV light.
UV light. Okay. So to understand it, let's see this, the wavelength of light. Okay. I think you must be aware about Rayleigh criteria.
Mm.
Okay. So it says that the minimum thing, the minimum resolution, or the minimum thing that you can see using a specific light is somewhat dependent on the wavelength of the light,
Yes.
right? So you see, using visible light, the maximum resolution we can go will depend on this, right? And 10 to the power minus 7, that means somewhat in this, not even in nano, right? Nano is 10 to the power 9, minus 9, right? So we go for ultraviolet rays, okay? It is like I said 365 nanometer and 465, or I think 456 nanometer is there. Yeah, these are the resolutions that we use. Okay, but suppose we want to go beyond this. We want to have lower resolution. Like we want that our feature. If we are using 365 or 56 nanometer, what is the maximum feature size we can get approximate? Rayleigh criteria something like 2 lambda. Do you remember this? 2 times the lambda is the resolution generally. There are it is not exactly the thing that I am talking about. There is a proper calculation where you can find the exact resolution. Okay, so approximately we can go till 600 nanometer. This is the minimum resolution we can get using these devices, 600 or 800, something around that. Okay, what if we want to go lower than that? Then we can go for X-rays, and even lower than that, gamma rays. But gamma rays are not suitable because they have very high energy and they can destroy the sample itself. We can like UV also is divided into UV and deep UV. Okay, there are some lithography which are now being used as deep UV. Okay, they have lower wavelength than this. Okay, they are used, and X-rays can also be used. But the problem with X-rays is that they are very costly. If like X-ray, we are using of very low intensity for this imaging and all. If we are using for photolithography, and that also the whole X-ray machine is used for this photolithography, it will be very costly compared to the UV photolithography. Okay, that is why the best resolution we can get using X-ray, because blue light is visible, it will have higher wavelength. IR light is even higher than our visible light, UV light and X-ray. Between this, X-ray is having lower wavelength. Okay, lower wavelength equals to higher resolution. Got it?
Yes, yes.
Okay. So whenever such question comes, always remember the Rayleigh criteria. The lower the wavelength, higher will be the resolution, because we will be able to resolve lower dimensions. Right? Okay. This should be question 22, not 21. Okay. The smallest feature that can be printed with adequate control using photolithography is controlled by smallest image that can be projected on wafer, resolving capability of PR, temperature of wafer, energy of ion implantation beam. It is again about resolution. So, which of the following features will determine the resolution or the smallest size we can print using photolithography? Yes, any idea?
No, sir. Is it the energy? Because capability of PR, smallest image, that can be, that is not possible.
Energy,
Temperature
like in photolithography, we are not using this.
or temperature, or maybe no.
Like, remember the process of photolithography. It is talking about photolithography. Okay,
Yeah, in implementation beam is not the that is not a step in the photolithography.
photolithography. Yes, neither is the temperature. Like
No, no.
exposure and this, we are not putting
Yes, yes.
like temperature is not there, right? So these two are discarded. So what about these two? First is the smallest image that can be projected on the wafer. So if the light
That
is
is,
capable of projecting very small images, then we can get very small, right? If the light itself is of the higher wavelength, we cannot get that, right? That we have discussed in the previous question itself, right? So first will be true or false. Hello.
yes, yes. Listening. I'm just thinking on it.
Yeah, sure.
No idea. I'm not able to get the question itself, smallest feature that can be printed with adequate control using photolithography.
So
Smallest
forget about this adequate control. Like everything is ideal. If everything is ideal, what are the parameters that will determine what is the smallest feature size we can go for? First is the smallest
First
image that,
cannot be possible because it is then smallest image that can be projected on wafer, right?
hmm,
So if my structure is an image, means that is nothing but a mask, right?
yes,
So
yes,
it may possible that I may have a requirement of larger structure.
yeah. So it is what is the smallest limit we can go for? We have larger structure, it's fine, but sometimes we need very small structures. In that case, what will be the determining factor?
Then first only, then how much what we can project on the wafer.
Yes, so the smallest we can project, and that will ideally depend on the
So yeah,
source of light. Okay, and
source
then
of light is
yeah,
very true.
then there is one more factor that I was discussing earlier also. What if we have the capability of going to till say 100 nanometers, okay, structure. But the problem is that our photoresist itself is say 4 micrometer, okay, and we want to cut it in uh, like we want to resolve it to a dimension of 100 nanometer. Will it be possible? Like the thickness of the photoresist itself is 4 micrometer. So what will happen is that there will be a lot of refraction in these things, and we'll not be able to get such smaller
No.
dimensions.
Hmm. Hmm.
So the resolving capacity of PR is very important when you are going for smaller dimensions. Sometimes it happens that we have very good instruments, but we don't have a PR that can go to that smaller, like that thinner layer. Okay, like if we have thick photoresist, okay, we cannot create or carve out very small features from that. Okay, because this small like 100 nanometer kind of feature will it get somewhat like if there is a distance of 100 nano like say let me like I want to create a feature like this, okay, and the gap is say 100 nanometer, getting it? So and I have a light source of say I have a light source of 50 nanometer, which is very high actually, very high energy and all, 50 nanometer. But our resist itself is say 1 micrometer. Okay, so when we will expose it with light, it will not cut it like this. It will go somewhat like this. Okay, the penetration of light will not be very uniform since this is a uh, reflect like that is a very viscous material and all. Optical transparency is also not there. Okay, we are uh, exposing it using some energy of the light, like, and since we are going for high energy, low wavelength, okay, so we will not be able to resolve. So what will happen is that the structure that we will get will actually merge together. Are you getting it?
Yes, just trying to understand. Yes.
Yeah, a bit like it is very much dependent on this, and this is a fact that many people ignore. Okay, they are not able to understand that sometimes what happens is that you have a high-end machine, okay, that is say able to, like, let's not go to that smaller dimensions, like general machines which are able to go till 600 nanometer, or say even say like 1 micrometer is the resolution, 1 or 1.5 micrometer. Okay, and what they will do is that they will take a thick wafer, thick photoresist that is having a thickness of say 3 micrometer, and then they will try to make a pattern that is separated by 1.5 micrometer. So you will say that I have good light source, I have good equipment, but why am I not able to get the like you were making some patterns like this, okay, and what you got is that these two patterns got merged. These two got merged. Why? Because the distance between them was less, and that less distance was not covered up by the instrument because the PR thickness was more, or maybe the resolution was not that much. Okay, so whenever we are going for PR, this like for photolithography, we have to take care of these things also. What is the minimum I can get? The one is it will depend. This will depend on the type of the instrument you are using, instrument or the source you are using, and this will depend on the PR you are using. Okay, so you have to take care of both these things. Getting it?
Yes.
Okay, so whenever we are going for photolithography, it is not only about the machine, like machine or the instrument that we have, it is also depending on the type of coating you are doing or type of PR you are. That is why PR plays an important for what purpose you are going to use. The PR can vary. If you like SU8, you will get very thick. SU8, you can get thick structure. Okay, so the resolution will not be higher in that case. For that, for higher resolution, you will have to go for some other photoresist. Okay, so these are the two things. Yeah, you have some question?
No, I said yes.
Okay. So small this we have discussed and this. So remember I was talking about HMDS that is used as primer. So sometimes we may need very thin coating of the photoresist, and that to assist that we use the primer. Okay, so that's all. Any other questions related to anything taught, or apart from this anything in the course also you can ask?
Okay. Okay, that we just discussed. Na, silicon nitride is used to compensate the stress, right?
Yes, yes,
So as it is helps to compensate the stress in the cantilever, that means it also creates some stress. Then because of that stress only, it is helping to compensate it. That
yes.
means it
So
induces the stress, right? It also
yes,
induces the stress.
so like there is some stress due to SiO2, like that can try to bend it. Okay, and another stress we are putting exactly on the opposite direction, you can say, that will compensate it and make it straight. It
Okay.
is like
Huh.
one stress above another, so they will cancel
Uh-huh.
it out.
Okay.
Okay. Any other questions?
No,
Okay. So that's
till
all
now
for today.
nothing is there. So
Okay.
maybe next time.
Yeah, you are free to ask anytime, not an issue.
Yeah.
Okay. So that's all for today. See you
Okay.
in
Thank
the
you, sir.
next class. Okay.
Yeah.